Hi, welcome to our video on running the supplied Python examples. Rather than be a complete course on programming with Python, these examples can be regarded as a cookbook or recipe book that you can remix to solve many data science related problems. I've already gone ahead and extracted the Python CLI gzip tar file that I shared with you using the course management system. Before running our first Python program, it's a good idea to make sure that our Python environment is configured correctly. What I can do is I can echo the path variable that's built into Bash to make sure that the Anaconda2 bin directory is the first one that appears within the path. What I can go ahead and do then is I can execute my first Py program named first.py by running Python and then the name of the Python program I want to run. As this suggests on line 6, all of our program's code is just simply to print the statement hello world. The rest of these lines are comments and they're only meant for the human reader. The very first line here tells the operating system where to find the Python interpreter. That's to let us execute our Python program as if it was a built-in Unix program, in effect without using the Python interpreter directly. The way we can do that is by changing our Python program to be executable by using chmod u+x and specifying the name of the file which we want to change the permissions of. So notice here I've listed all the files here, including first.py, and it does not have the X permission for execution set. Once I perform this action and I list the files in the directory again, we see that first.py is now both highlighted green and it has an X for the user's executable permission set, which means I can execute first.py from the command prompt by typing / to indicate the current directory, and then just simply the name first.py. Most Unix systems will require you to type / to indicate that you mean a program in the current directory. The reason that we can execute first.py without specifying the Python interpreter is that this very first line here tells the operating system where to find our Python interpreter. What we can also do is we can change the name of our file so that it doesn't have that .py extension. One way I can do that is by copying first.py to a new name called hello. If I list the files in my directory, we see that hello is one of them, and I can run it, the command prompt, just by typing its name. In our second example, called variable.py, we show how we can prompt the user to enter information such as their name and age and store those values in variables for later use. Note here that the name is used directly, but the age is first converted to an integer or whole number before being stored in this age variable. On line 7 here, the difference between 90 and the user's age is computed, and then that value is used to display to the user on the following line how many years it will take for them to reach 90 years of age. You'll notice here that the variables name and diff are used to display their values to the user. Here we take advantage of the fact that our print statement that displays information to the screen, much like in the last example, can take a number of pieces of information separated by commas. And we also take advantage of the plus operator that can take a so-called string of text and concatenate it or put it end to end with another string of text, in this case containing the name of the user. Let's run this program to see how it works. When line 5 is executed, the prompt "your name" is printed for the user, and then it awaits the user to enter some information and press enter, such as their name. Once the user presses enter, the data that they entered is stored inside the name variable. Immediately after, this is printed for the user in order for them to enter their age. Once they enter their age, it's going to be converted to an integer and stored in the variable age. Once the computation is complete, this message is displayed to the user to show them how many years it will be before they reach 90 years of age. Notice that this equal sign is not the mathematical definition of equals. Its technical name is the assignment operator, and what it does is it evaluates whatever is found on the right-hand side and stores that value in whatever variable is found on the left-hand side. What this means is that later on in my program, I could reassign some value to that variable and it would take on a different value. This is actually a very useful feature that we use throughout our Python program. The if-else.py example demonstrates several concepts, including so-called selection statements, including if, else, and else-if statements. This program also demonstrates how to use the sys system library to handle command line arguments entered at the terminal. It builds upon the previous example of variables.py. In this example, we use selection statements and logic to respond to user choices made at the time the program was started via command line arguments. Recall command line arguments to programs. Examples include the -l at the end of ls-l. Other examples include the -xvf options when tar is used to extract a file or directory. Command line arguments are a common way to specify the precise behavior of command line or terminal programs. Here, we import the system library on line 1, which gives us access to system features such as the data passed from the command line. This program expects that if the user supplies a first command line argument, it will be understood to be the user's name. Also, this program expects that if the user supplies a second command line argument following the first argument, it will be understood to be the user's age. The logic to handle checking whether the user's name was entered at the terminal as an argument is implemented by the first if-else statement encountered in the program on lines 9 through 14. Recall that if statements execute the indented code only in the case that the condition here is true. The if statement on line 9 checks to see whether the length of the arguments provided at the terminal is more than 1 by using this len function. The len function returns the length of sys.argv, which is the list of command line arguments provided by the user at the terminal. Remember the len function for later. It will be used to determine the length of other lists that we encounter. sys.argv is a variable or object that contains the list of command line arguments entered by the user, accessible by index starting at 0. The first or 0th element of this sys.argv contains our Python program name itself and is not useful to examine here. If this condition on line 9 is true, that means that the user has entered their name as an argument. Therefore, here on line 11, we assign the user's name, stored under sys.argv index 1, to our variable on the left-hand side here, which we conveniently name name. The indented code following the else is executed only if the condition on line 9 is false. And this code asks the user to enter their name using the supplied prompt as we did in the previous example, variable.py. The second if-else statement encountered on lines 15 through 18 in the program checks to see whether a second argument has been entered by the user at the terminal. If it has, this argument is available under index 2 in sys.argv. It is converted to an integer before being stored in our variable conveniently called age. Similar to the previous if-else logic relating to the user's name, this logic here will ask the user to enter their age with the supplied prompt if the user hasn't entered it at the terminal. This program's logic from line 20 onward displays a different message to the user depending on the user's age. Here on line 20, the condition says that if the user's age is exactly 90, the following message will be set: you are already 90 years old. Notice that the else if condition on line 22 will only be evaluated or checked if the condition on line 20 is false. In the case that the condition on line 20 is false and the condition on line 22 is true, then the indented statement on line 23 will be executed, which will set the message to tell the user that they will be 90 in the appropriate number of years. The statements indented following the else statement on line 25 will only be executed if all the above conditions are false. The statement on line 26 will compose a message telling the user that they turned 90 a certain number of years ago. Notice that the final print statement here on line 27 actually displays the message that is composed of the two variables set earlier. Say hello on line 19 using the user's name, and then the message relating to the user's age is composed on lines 20 through 26. Here on lines 23 and 26, the str function is used to convert the numerical result of this computation into a text string so that it can be added or concatenated with the rest of the message using the plus operator. It should go without saying that if you're curious about Python programming, you can try changing any of the programs I've shared with you and run them. Individual lines of code can also be tested using Python's interactive mode, IPython, as demonstrated in class. For now, let's try running this program to see how it behaves. Notice that when I run the program, it's going to behave differently depending on how many arguments I supply at the command line. It will also behave differently depending on the age I supply. Boy, I look forward to teaching this course when I'm 95. One of the takeaways from this program is that the processing of command line arguments can become tedious for every program. Fortunately, Python provides something to simplify this called opt-parser. We're going to see it in use in the coming examples. The program whileloop.py demonstrates important Python features such as the repetition of statements using a while loop, as well as generating unpredictable so-called random numbers or pseudo-random numbers using the random module or library imported on line 1. On line 3, we generate a pseudo-random integer between 1 and 10. On line 5, we see a while loop that repeats the indented statements as long as the condition on line 5 is true. In this case, the loop will continue as long as the user has not correctly guessed the secret answer generated by the program. Each time through the loop, the program asks the user to input another guess. Then it compares that guess with the randomly generated answer. In the case that the guess is incorrect, the program prints wrong. Once the end of the loop is reached here on line 8, as it is the last indented statement, execution returns to line 5 where the condition is checked again. In the case that the guess was correct, this condition becomes false, and execution resumes on line 9, where the user currently receives a short message indicating that their guess was correct. Let's play the game. Notice that every time we run the program, the secret number generated is potentially different. Last time the secret number was 1, this time it is a different number. It was 7. There is such thing as an infinite loop, which is a loop that is set up in such a way that the condition never becomes false. This can either be done on purpose or by mistake. Can you think of any programs that you might want to run forever? Try uncommenting these last 4 lines of the program and see what happens when you guess the first part of the game correctly. Remember, you can always press Ctrl+C to terminate any Python program that's currently running. In forloop.py, we demonstrate another kind of loop or repetition structure in Python called the for loop. The for loop in Python is a loop that is more adapted to performing an action on every element of a list in a set order. On line 5, we get the user to input a list of numbers separated by spaces. Notice that the user prompt is composed by using the plus operator to add strings end to end and using the str function, which is used to cast or convert numerical values to text strings in order to be displayed. Converting types sometimes happens automatically or implicitly in Python as needed. On line 8, we split the text that has been entered by the user into a list. We refer to this list using a variable named tokens. The for loop on line 12 can be read as, for each token in the tokens list, perform the indented actions. This logic on lines 13 through 20 validates each token as a valid number between the lower bound 3 and the upper bound 30. Notice that we are converting each element of the list to a numerical integer value for comparison on lines 15 and 17. We can run this program on a list of valid and invalid numbers to see how it handles that input. Notice that for each piece of data, it determined whether that number was valid, too small, too big, or not a number. The for loop is often used in conjunction with the range function that can be used on the spot to provide a list with the appropriate bounds. Let's investigate the range function using the interactive Python shell, IPython. Here I'm just going to display the result of creating an arbitrary list between 13 and 39. And I'll demonstrate how we can use it in conjunction with a for loop to display those numbers. As mentioned in earlier examples, dealing with arguments provided to a program from the command line or terminal is both a common and potentially tedious task. The opt parser module or library can be used to simplify the processing of command line arguments. This program uses option parser to systematically allow the user to enter a name and age with the same basic logic as if-else.py. But in this case, we use opt parser to handle the command line arguments in a more robust and feature-rich manner. On line 10, we specify that the program will accept a command line argument indicated with -n at the terminal. Alternatively, the user could type out --name followed by their name. If they forget to type out their name, then this prompt appears. We're going to test that out in a minute. If the user supplies their name using this command line argument, then the name is stored under this specified destination key. If the user did not supply their name or age, the corresponding property will be set to none, which we use later on. The user's age is handled similarly to the name. Here, because age is a numerical value, we just indicate that its type is int at the end. In this code here, in lines 15 and 18, we examine to see whether the user inputted the name and age respectively, and if not, we prompt the user to enter it as before. Then what our program does is use the same logic as in previous examples to display an age-appropriate message for the user. Let's test this out with option parser. So first I'll run it without providing any command line arguments. Then I can try it by specifying -n and then my name. This time it just asks me for my age. If I type -n and I forget to type my name, I get this usage error automatically generated. Here I can also type --name followed by my name. I can also supply -a to indicate my age. So we got all that functionality just through this couple of lines here. A very common type of command line argument or option is a verbose option that can cause a lot of detailed information to be displayed for the user to learn more about what's going on in the background. For example, the tar utility does this. When we run the tar utility using the -v flag for verbose, we get our familiar output. If instead we were to run it without the -v flag, in this case, we see actually we get no output at all. The same thing happens in the background. The only difference is that we see a verbose output. This program, OptionParser2.py, illustrates how we can use OptionParser to introduce a -v flag or a verbose flag into our program. If we run this example, without the -v flag, we see only very brief output. Instead, if we run it with the -v flag, we see it prints out blah 10,000 times. How's that for verbose output? Ha 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 ha! Previously, we demonstrated in variable.py that we can store scalar data, meaning data that has only one value, using ordinary variables. So-called data structures are used to store more complex, multi-valued data. The three basic data structures or containers in Python that can contain multiple values are list, dictionary, and tuple, and these all have slightly different purposes, as we'll learn. We can run this list and dict.py example from the terminal in the familiar way, but I'm going to illustrate how each line works by running it in interactive mode Python. We've already encountered lists a few times in the context of lists of command line arguments. Lists are historically called arrays. You may also see that term used. Also, they've been referred to as vectors in the past. This example shows how we can store text data such as days of the week using a list. Excuse my terrible spelling. Notice that we can access individual values inside the list by using the square braces and typing the index of the day we would like. Notice how the lists are indexed starting at 0. The highest valid index for a list is 1 less than its length. Notice I get an error when I try to access the 4th element of the list at index 3. We can access the elements of the list, that is the values stored inside, once again by using these square braces, following the name of the list. As before, we can determine the length of the list using the len function. With ordinary scalar variables, the equal sign or assignment operator makes a copy of the value. Behold. In the case of our data structures, though, the assignment operator does not create a copy of the list, dictionary, or tuple. Notice in this example, there's only going to be one copy of the list in memory. Both variables, things, and days refer to the same list in memory. There are several built-in functions for working with lists. The append function adds an element to the end of the list, increasing the size of the list by 1. The insert function allows us to enter new information into the list at places besides the end. We can specify the position for the new data as the first argument to insert. This will insert this item at position 0 and shuffle the rest of the items to the right. We can use the extend function to add multiple items to a list. We can use the index function to find a certain value in the list. Let's say I wanted to find Thursday in the list. Oops. Here, I've forgotten the X in index. There we go. This gives us the correct index, 0, 1, 2, 3, 4. 4 is the answer. We can remove items by value by using the remove function. Everybody hates Mondays. Goodbye, Monday. We can return and remove an element at the same time by using the pop function. This will remove the item at the specified index. In this case, the item at index 1 is going to be the 3 question marks. Lists allow us to mix types, including putting lists within lists. We can also initialize an empty list by using the assignment operator and just an empty list as indicated by an opening and closing brace with nothing in between. We recognize that it's a list we're initializing because the square braces are used. In this assignment operation here, we're composing a new list out of the list of days and the list of dates. We can access individual elements of these lists. This is the list at index 0. This is the list at index 1, and we can access their individual elements in the following way. This will get me the list of days. Sorry, dates, because I used index 1. The days are at index 0. If I want to access an individual day, this would give me Thursday. Similarly, if I want to access other data, I use the appropriate indices. Now, turning our attention to dictionaries, we can continue within the same IPython shell or start a fresh one since these examples are independent. Dictionaries in Python are often abbreviated DICT. Dictionaries are key value associations or lookups. They're also called associative arrays, hashes, mappings, or hash maps in other languages. The main idea is that you can store and later access data by using a key rather than a numerical index, as we demonstrated previously using lists. We'll learn that any immutable type can be used as the key, including text strings and the tuples, which we will introduce later. Notice that with dictionaries, curly braces are used to initialize the dictionary, unlike the square braces for lists. Confusingly, square braces are still used to access individual elements of a dictionary, as follows. Here I'm using lowercase a as my index and alpha as the data I'm storing under there. Let's store some more data under there. Here I'm storing the phrase beta under the key B. This time I'll decide to type it out. Notice when I print the entire dictionary, it lists each key followed by a colon followed by the value. Each key value pair is separated by a comma. The entire contents of the dict are contained within these curly braces when they are displayed by default. As with lists, we can reassign values using the assignment operator. And also, like lists, we can store mixed types. Here we are storing strings and numerical values together. We can use the in keyword to determine whether a particular key exists within a dictionary. If we try to access a dictionary with a non-existent key, Python generates an error called key error. By using the in keyword, we can guard against generating these errors by accident. Here we don't anticipate any output because Z will not be in our dictionary, so we won't have anything printed. Notice we didn't get the error here. A safe way to try to access data at a key and we're not sure it exists is by using the get function. Oh, here I mistyped it. Actually, we have to use round braces. That's an easy error to make because get is a function rather than trying to access it using the square braces. So get is a safe way. If we want to use a for loop to iterate through the keys in the dictionary, can write something like this. The equivalent syntax to the above is to type out keys explicitly. Oops. Here, in the line above here, it's assumed that we're using the keys to iterate. If we wanted to return all of the keys that are used in the dictionary, we could also use dict.keys. If we want to see all the values, it's dict.values. If I had a different name for my dictionary, I would use it instead, right? The idea here is we can have multiple dictionaries. Down here towards the bottom of our dictionary examples, we see this code that is very reusable and useful for visiting each key in the dictionary in an ordered manner. In this case, they're sorted by alphabetical order. If we want to quickly see all of the different items stored in our dictionary, we can use dict.items. Last but not least of the data types are tuples. Tuples are very much like lists, except that they're immutable, which means that their values cannot be changed or reassigned to anything else, unlike lists and dicts. Let's show this in action. Notice that tuples are initialized using the round braces, unlike lists, which are initialized with square braces, and dictionaries that are initialized with curly braces. We can actually reassign the entirety of values to be this new tuple here, 1, 2, 3. Right? But I cannot reassign the individual values. Values 1, here I can try to reassign to 5, and it'll actually give me an error. The tuple does not support reassignment. Text data represented in a string behaves very much like a tuple composed of character data. We showed in the file.py example developed in class that we can access individual elements of a string by using its square brace notation. However, we cannot reassign any individual elements of the string, much like the tuple. Here, we revisit option parser for a minute in order to demonstrate a point in the list and dict2.py. And that is that lists and dictionaries underlie a lot of the common functionality in Python. Here, the parser's options are represented as a list, and the others are represented as a dictionary. It's common to realize that certain code is repeated often, for example, the computation of mathematical functions. Python allows us to define such reusable functions by using the def keyword. In this example, we define the mathematical factorial function recursively in terms of itself. Notice that in this program, function factorial.py, execution of the statements doesn't begin on lines 4 or 5 or anywhere within this factorial function. Execution begins on line 14, following the indented code for the factorial function. In the bottom part here, we get the user to enter a number, and then we compute the factorial of that number by passing the number entered into our factorial function. We use the name of our function, followed by round braces, and we put the appropriate arguments between the braces. Notice that within the function, the argument that we pass can take on a different name. We pass the value of number, and this value takes on the name n within our function. Whatever the value's name was when it was passed to the function, it'll be referred to as n within the function. As in many mathematical functions, Python functions can provide a computed value back to the caller. In this case, the return keyword is used to indicate what the value computed by the function that is to be returned. Beyond computing purely mathematical results, functions can be used to encapsulate common or repetitive tasks such as getting input from the user. This example does just that. Function inputNumber.py defines a function that specifies a prompt and gets the user to enter a number within the provided bounds. We can load a Python file from within IPython by typing load and then the name of the file. So I'm just pressing enter and I get my prompt here in 3. This way we can bring scripts that we have previously written into our environment. Now we've created the input number function that accepts as arguments a prompt that will be displayed to the user, a minimum acceptable value for the input, as well as a maximum valid value. Here, let's use it to force the input of a number between 1 and 10. Minimum 1, maximum 10. Here I'm provided with the prompt. And what this ensures is if I enter a number that's too small, or too large, or something that's not even a number at all, my function input number keeps looping using this while loop until a proper number is entered within the bounds. Here, what it's being done is the return value that's provided by that input number function is being assigned to the variable that I've named entered value. let's take a look at line 12 of the function input number.py. I want to talk about this special way that we're using the print statement. This is what's called formatted input. In this formatted style of printing, instead of stitching output together using commas or the plus operator, we leave placeholders for variables within a formatting string. These placeholders, which are each preceded with the %sign, are placeholders for values that appear later in the print statement. %i, as we see here, is a placeholder for an integer. %f is a placeholder for a floating point or fractional value. And %s is a placeholder for a string. Following the end of this formatting string, we see another %sign followed by a tuple. The values in the tuple each correspond to the placeholder in order that appears in the formatting string. Notice that we have to have the same number of placeholders in the formatting string as we have values in this tuple. Functions can also be used to make programming and debugging tasks easier, as in this example of function logit.py. In this example, the logit function is defined to help the programmer display formatted debugging information. This next example, url.py, demonstrates that Python has very powerful libraries and utilities, such as urllib, that allow us to interact with web APIs over the internet in order to pull down unstructured Web 2.0 big data sets for processing and eventual analysis. This example shows how after a few seconds, provided we have an internet connection, we can read data from Google Trends. The processing of the returned data is left as an exercise for now. The shell example 1.py program demonstrates an interesting connection between the Python environment and the Linux command line environment that we've discussed earlier. By using this subprocess library or module, we can call any Unix command from within our Python program and display the results. In this example, we call the ls-l command using subprocess.call. In this shell example 2, we extend the previous idea to show that we can also read the process's standard output using this for loop found on line 7. In this example, we merely print out the output, but we could also store it in a variable, list, or dictionary for further processing. In this example, we're catting the contents of the previous Python program and printing it out line by line. In this shell example 3_demo.py, we see a useful example for your assignment because it demonstrates how to read from standard input so that your Python program can work within a Unix pipeline. Wouldn't that be cool? For this example to work properly within a Unix pipeline, we have to make sure that this is the correct path to your Python interpreter. Also, unless we want to explicitly invoke the Python interpreter each time, we have to make sure that this file is executable by using chmod u+x and then the name of the file. we can verify that it's executable by running ls-l. We see on this line that its X permission is set, which means that we can execute it. Taking a look at the code, we see something kind of interesting on line 13. There's a check to ensure that this code isn't running from within the Python interactive environment, such as IPython shell. You will not usually need a check like is shown on line 13 unless you really want to be thorough. Line 15 initializes an empty dictionary which is going to be used to store the data as it is read in. The most important part of this program is lines 17 and 18 that show a reusable chunk of code that reads in one line at a time from standard input, stores that data in a variable called item, and then on line 18 it removes any new lines at the end of that data using the .strip function. Take a look for yourself what difference this will make by commenting out that line with the .strip and see what difference it makes when you run the program. Here, the variable name item is just that. You can use a different name of your choosing. Just make sure that you're consistent with that name throughout the rest of your program. What this program does is it counts how many times an item is mentioned in a list which is read in from standard input, one line at a time. There is a provided data file called animals.txt that has some input data that has one item per line as required. Let's run the program with the provided animals.txt file. So here I'm composing a Unix pipeline. I'm catting animals.txt and I'm going to read in that data from standard input line by line using shell example 3.py. Notice that elf and cat appear multiple times. Once the contents of animals.txt are piped into our script then counts the number of times each item is encountered in the input. The key to how it does this is on lines 19 through 22. The if statement checks to see whether the item has been previously encountered. If it has, this code here increases the count by 1. Otherwise, this else statement handles the case where we're seeing that item for the first time. In this case, we initialize the count to 1 because this is the first time that we've seen that item. The for loop on line 25 is not indented with respect to the first for loop on line 17. Therefore, this second loop executes after all lines of standard input are processed. What this second loop does is it prints out each item. Notice that we can iterate over or visit each item in the dictionary by using iteritems, as we did before. The formatted output on line 26 says to print a decimal value, followed by a tab, followed by a string, followed by a new line. The placeholders here are filled with the item count and item name, respectively, which is why we see the output we do when we run the program. The key takeaway here is whenever you want to read from standard input in a pipeline, you can reuse these lines of code. In this example, we demonstrate how we can create a simple scatter plot using a Python module called matplotlib, which is specialized for making plots and charts. Previously, we were having some issues with this example and importing matplotlib. For example, if I try to run it, we get this error that we cannot find pyplot. The reason for this is actually kind of silly and not obvious to begin with. The problem that we're having is that we've named our source file matplotlib.py, and from within we are also trying to load or import matplotlib. So here is an example of a name collision. We've named our program the same as one of the Python libraries. The simple fix for this is just to simply rename our Python example to plot.py. The lesson here is to be careful in how we name things. That can have an impact. What this script does is it defines a plotting function that we name pu, and this function accepts a name for a plot as well as a list of x values and y values to plot against them. To test this program, we can uncomment lines 15 through 17, or we can load it from within IPython. Recall I've renamed matplotlib.py to plot.py, which is a friendlier name. Let's go ahead and define some x values and some y values to plot against them. Here I've forgotten my assignment operator. There we go. Finally, I can call my plotting function pu, and I can pass the data I want. First, the title, my first plot, x values and y values. Here the plot shows up in a new window. I can save this plot by hitting this little savey button, browsing to wherever I want to save it, name it to what I want, and hit save. The figure is available on the desktop like any other file. You can attach it, print it, email it, anything you want. Once you're done with the figure, you can press the little X to close it. Classes are a rigorous way to model complex data by creating your own custom data types with built-in operations that you define for your type. In this example, we define a part class, which could be used to represent a part in Canadian Tire's inventory database. Lines 9 through lines 51 model or define what it means to be a part in our database. The word method refers to a function associated with or bound to a class or data type such as our part. The different methods associated with this part are a display method, an input method, a save method, and a read method. These are the operations that each part supports. The data associated with each part are referred to as fields. This part has 4 fields: a name, a numerical ID, a height, and a length, which are pieces of information that you might want to keep on every part in your inventory. The code on lines 63 through 79 show how we can create new instances of our part class and use the various methods defined in the part class. You will encounter classes and objects throughout your data science journey. We could spend an entire course on the details of using classes for programming. That's a topic called object-oriented programming. Let's run this example to display how it works. One more note concerning math operations within Python. Notice that when doing numerical division, we might be tempted to assume that this is going to give us a real number division. However, Python has a rule that when you have an integer divided by an integer, it's going to perform whole number division. In order to force real division, one of the two numbers has to be what's referred to as a floating point value or a fractional value. So if I turn one of these into something with a decimal point, we see that now we have the exact or real division. When dealing with variables, we also do whole number division if both of the variables are whole numbers. One of the things we can do in order to force one of them to be treated as a real or fractional number is just simply cast it to float. Now we again get the real number division. Another option might be to multiply one of them by a floating point value. That again yields us floating point division. Other times, you may wish to force whole number division, in which case you can cast both operands as integers, and that will perform whole number division. That's one more thing to pay attention to when doing math operations in Python. Do you remember file.py that we developed in class and we left as an exercise for you to implement reading from standard input when the user does not specify a file name to read from? Well, let's actually go ahead and implement that now, as promised. I mentioned that shell example3 _ demo.py contains a useful little code snippet for reading from standard input. I'm going to go ahead and copy it, and I'm going to drop it into file.py near the end here, so that I can read from standard input. Oops. And if I want to process standard input in the same way that I'm processing the line from the file, I'm going to go ahead and drop in that same logic or text or code in order to accomplish the same processing. So let's go ahead. I'm going to rename this program file2.py because it does something slightly different. This version actually reads from standard input. ahead and run it from our terminal. So I'm going to say cat animals.txt. I'm going to pipe it into this reads from standard input, and it complains that line is not defined. Let's go and fix that in here. Here I copy and pasted, and we're using the name item to represent the line. One thing to be consistent is we can just use line, the name line, to represent the line that we're reading from standard input. That's going to fix our immediate problems. Let's try running our program again. This time it works. Our program is able to read from standard input. One thing to note here is that the code for processing the text as it's entered from the file or from standard input is virtually the same. That's a good opportunity to write a reusable function in order to handle processing that text. Let's go ahead and do that now. Def, I'm going to define a function, process text, and I'm going to accept some data here. I'm going to accept the string to process. So here I'm just going to name my string data. So what I'm going to do inside my process text function is I'm going to basically do this processing code regardless of whether it's coming from the file or from standard input. Just fixing our indentation here. And notice now, based on our understanding of functions, the name data is going to be what we are working with here rather than line. Then down here, we just simply call our data processing function, process text, with the appropriate data. So in this case, we're passing the line that we're reading from the file, and in this case, we are going to pass the line that we've read from standard input. I'm going to save this version as file3.py. This version is better than the other version because if I ever have to change how I process my text, then all I need to do is change it in one spot rather than trying to maintain the same code in two spots in my program. Let's go ahead and give this a try. Remember, I saved my newest program as file3.py. So it reads out of standard input. Let's try it. We can specify -f and then the name animals.txt as the input file. You'll see it works as well. I'm going to share these versions with you on the CMS. Thanks for tuning in.